I'm just going to go ahead and get started since most of you guys are here already. So hey everyone, I'm Angela and welcome back to Earth Science. So today's topics will be the atmosphere, wind, and some erosion. So just a little disclaimer, this class doesn't cover the complete scope of Earth Science. There's a lot of not more necessarily, but there's a lot of important topics that I won't be covering. So if you guys find my lectures interesting, then I encourage you to explore more on your own. And some topics that I think are important that I won't be covering include like glaciers and currents. So I'll just get on with our first topic of the day, which is the atmosphere. So this is a chart of the composition of the atmosphere. As you can see in this pie chart, most of it is nitrogen, and then it's followed by oxygen, and everything else is within the last 1%. So in this chart, it looks like there's like a lot of stuff, but actually everything from here and below is less than 1%. So I'd say the important things to remember is that nitrogen is the most abundant, and then it's oxygen, and then you probably should also remember that argon comes next, even though it's only 0.9%. And you might be wondering where water is on this chart, and I also don't know why it's not on this chart, but usually it would be about 0.4%, and at sea level it would be about 1%. Because the water content in the air can vary depending on location. And just a side note, you probably recognize carbon dioxide and methane as greenhouse gases. So these are gases that can like basically trap heat, and that raises global temperatures. And something cool, I guess, is that water is actually a very powerful greenhouse gas. I think it accounts for most of the greenhouse effect, actually. But the reason why people aren't going like, oh, there's too much water in the atmosphere, and it's global warming, it's bad, that's because water is condensable. So like once there's a lot that accumulates in the atmosphere, it can actually like rain. So there is no continuous buildup, which is why we're not complaining about it, global warming. So next topic would be air pressure. So air pressure is essentially the pressure caused by air, and pressure is defined as force over unit area. So air pressure can be measured using barometers, and there are two main types. They have mercury and aneroid. So the mercury barometer is the most intuitive and like textbook example. So the design is just to have a dish of mercury and a glass tube that has a vacuum. So there's just like nothing in here. And so atmospheric pressure will push down on the mercury, and then it will up in the tube. And it rises up 760 millimeters at sea level. So that's where this unit comes from, 760 millimeters of mercury. So Hg is the atomic symbol for mercury. That is equivalent to 1 atmosphere, which is like probably the easiest unit to understand. It's the amount of pressure, like it's 1 atmosphere's worth of pressure. And this is also equal to all these other values, which I'll be talking about a little later. So this is a little interesting unit. The torr is actually defined as 1 millimeter of mercury. So they just felt the need to make another unit. They're completely the same. So yeah, just note that this is a thing. And another unit that is often used is the kilopascal. So the pascal is the SI unit for pressure. It's defined as newtons per square meter. And the reason we use kilopascals is so that the values are easier to work with. So it's not in the 100,000s every time. And so these units are what you probably will encounter when you're doing like chemistry, and it's like gas laws and other gas pressures, you would probably use these. And these units over here are more related to weather. So you can see there's the pounds. It's like not traditional science because it's like American units. So here you have inches of mercury per square inch. This is pretty easy to like visualize. It's probably one of the easiest if you don't know any of the other units, because you can just imagine there's the square inch and the air is pushing down with 14.7 pounds worth of force on just that square inch. And another useful unit for weather is the millibar. That's actually defined as 1 hectopascal, so it's worth like 100 pascals. And I'll bring your attention back to this other barometer. This is the aneroid barometer, and it is made up of some like a metal chamber, and there's metal springs inside that will like change length slightly depending on the pressure, and that will move this little needle around, and that will tell you the measurement. And I like to add something about the mercury barometer. So the reason why mercury is used is because it has a high density. So it can actually, it moves up a reasonable amount. So like if you think about it, 14.7 pounds per square inch, like that's a lot of force. So if you were to use water, for example, mercury, the atmospheric pressure would push it way up, and it just wouldn't be practical to like read the markings. So next important topic of the atmosphere is the layers. So the layers are defined by mostly by the temperature, because you can see that this like wiggly line, this represents the temperature. The temperature, like how the temperature changes with respect to altitude, switches with each layer. So that's something cool to note. So I'll just talk about this going from the bottom up. So first layer is the troposphere. That is where all the weather occurs. So this little cloud, thunder, lightning thing symbolizes that. And the troposphere is also where just most stuff, like most people hang out. So there's parachute jumps and hot air balloons, and Mount Everest also goes within this layer. So the troposphere, the temperature decreases as altitude increases. So this is like pretty intuitive, I'd say. So like if you just think about it, if you're like in a plane, for example, and then it's like going up, and if the plane is cool and it has those like temperature readings, you can actually see the temperature decrease as you go up, and that's pretty cool. And so the commercial aircraft stays around this level. And the next level is the stratosphere. So the stratosphere has the ozone layer, and the ozone layer is made up of ozone, or O3, and that absorbs a lot of UV light, and that in turn that will protect any organisms living on the surface from extra UV radiation. And something to note is that there are some like man-made chemicals called chlorofluorocarbons. So just like the name, they're like carbon, they're made up of carbon, chlorine, and fluorine. And those can be found in like aerosols, or those sprays, I believe. And that has caused a hole in the ozone layer above Antarctica. And so because there's a hole there, there is less protection against UV, and so that can cause increased amounts of skin cancer. So that's bad. So we want to restore the ozone layer. That's a pretty important part of environmental science. And the mesosphere is the next layer. It is where meteors burn up. So because the air kind of thins out the higher you go, this is the first layer, starting from the top, where the atmosphere is thick enough for meteors to burn up. And that is a good thing, because if we didn't have the atmosphere, the meteors would constantly be like crashing on the Earth, and that would be bad. So the next layer would be the thermosphere. There should be an S here. It is where spacecrafts usually hang out. So it kind of ends at this 600 mark. So the altitude markings or altitude, like these definitions, kind of vary between sources, but this is like around where it stops. And then the final layer would be the exosphere. The exosphere is like the most space-like, so it kind of just fades out into space. Some people don't even consider it a part of the actual atmosphere, because the air molecules are just so far apart and just so thin. So this is where satellites hang out. So this line just splits this, just by the way. Yeah, so space shuttles and spacecrafts go thermosphere, and satellites go in the exosphere. So now I'd like to talk about the temperature thing. So as I said earlier, the layers are mostly defined based on the temperature patterns. So the troposphere, the temperature is decreasing with altitude because it is being heated by the ground mostly. So the ground has absorbed radiation from the sun, and because this layer is the closest to the ground, it is being heated from the bottom up. And then the stratosphere is heated by the ozone layer, actually. So the ozone layer, because it's absorbing a bunch of UV light, that actually heats up the stratosphere, so the temperature increases with altitude. And a little side note, when ozone is found in the troposphere, so when ozone is down here, it's usually because of some reactions with some pollutants, and that can actually cause global warming because it can act as a greenhouse gas. So tropospheric ozone is actually bad. That's something weird to think about. And then for the mesosphere, it goes, the pattern is like the troposphere again. So it is being heated from the bottom up, so the temperature is decreasing with altitude. And the thermosphere, because it is basically the layer that is closest to the sun, that aside from the exosphere, so it is being heated by the sun mostly, so the temperature increases as you get closer to the sun. And the exosphere, the temperature kind of continues to increase. It gets to like thousands of degrees. So this scaling would have to be like, ooh, so it goes like all the way out. And something cool to note is that even though it's like thousands of degrees, like up here, you imagine space as being cold. And so it actually feels cold to your skin because there are so few air molecules and they're so far apart. Because like temperature and like is the average kinetic energy of the molecules. And so if they're so far apart, they're not really like doing much to each other. So it actually feels cold. So that's like weird, right? And these pauses indicate the spaces, or like when one layer ends and one layer begins. So the tropopause comes after the troposphere. Stratopause is after the stratosphere. Mesopause is after the mesosphere. And there's no thermopause because the temperature doesn't switch back into like decreasing with altitude. And then aside from these like 5 main layers, you can also include the ionosphere. So that is around the area of the mesosphere and the thermosphere. And this is where the polar lights happen, or auroras. So the molecules are being ionized by the sun's radiation, and they can actually emit light for example, and here it's green or pink. The ionosphere is also responsible for the radio communication. So this is why like radios work, for example. And lastly, we have the homosphere and the heterosphere as ways to divide this. So the homosphere, as the name suggests, is homogeneous, and the heterosphere is heterogeneous. So homogeneous just means like evenly mixed throughout. So there's a lot of air turbulence down here. So that is why everything is evenly mixed. Whereas in the heterosphere, the molecules are layered by molecular weight. So the heavier ones go at the bottom and they get lighter and lighter. So there isn't much turbulence up here. So the layers still stay. So